All right, so what we did last week was we took this fat and we realized that as you add more drink mix, the molarity goes up, right? Because you're adding more moles of things to the same amount of water. And that at some point, that water has had all it can take and that it can't take anymore. And we call that a saturated solution. So as I keep dropping this in, there's a point right there at 5.9 molar, 5.96 molar, where it doesn't matter how much drink mix I add, it just stops going in. And I can get it back maybe by adding some water, right? Diluting it. So now I got it back down. So now there's more water to take more drink mix. So the other thing that maybe you realized if you played around with this a little bit is that different substances have different maximum molarities. KMNO4, potassium permanganate, much lower than the drink mix, 0.48 molar versus that was like 5 point something, right? We can do copper sulfate. Same phenomenon. As you add more, the concentration goes up, the color gets darker. So you all did pretty well with that on your Google Forms. But there's a point where the water can't take anymore and it's saturated, and anything I shake in just goes right back to the bottom. And the only way to make it continue to take stuff is to dilute it. But basically, this 1.38 molar is the line where copper sulfate won't go in anymore. So if I get that a little bit below, right, I can get back up to 1.38 and it'll be saturated again. All right, so that's what we learned with that. And so very quickly for this week, I just want you to know about solubility curves, which are these graphical representations of temperature versus solubility. As you can see, what I'll show you here is that gases are more soluble at low temperatures and solids are more soluble at high temperatures. The two things you need to know are saturated and the opposite being unsaturated. So while water can still take something to dissolve, it's considered unsaturated. When water gets to that point where nothing else can get into it, it's considered saturated. So when drink mix just drops to the bottom, that's a saturated solution. If the drink mix can still stir into the water, that's considered unsaturated. So on a graph like this, there would be a line, and that line sort of shows you where the saturation is. And as you can see here, the line for solids will go up as temperature goes up. So temperature is down here, solubility is here, and as the line goes up, the temperature goes up. And that's basically not surprising. You're giving more energy to the water to pull apart whatever it is you're drawing in there. So more energetic water molecules can pull apart things. Now remember again, what that's supposed to look like. It's supposed to look like this. This is what happens when we dissolve things in water. There's a solid situation, goes into the water, and then the water is able to pull apart its positive and negative ions with the positive and negative part of polar water. So if the water has more energy, if the molecules of water trying to pull this salt apart have more energy, they have more movement, right? More temperature, more movement. They're able to do a better job here of pulling apart these ions if these water molecules are moving faster and have more ability to pull something away. So it makes sense that the higher temperatures would have higher ability to do this for solids. That is not true for liquids, though. I mean, for gases. When you have a gas, the trend is the opposite. As you heat up the water, the gas actually decreases in its solubility. And that should make sense to you as well, because a gas wants to be a gas, right? It wants to float away. So if you give the system enough energy for water to be moving more, you're also giving energy for these molecules to move more. And because of that, as the temperature of the water goes up, when a oxygen molecule is moving more and gets to the surface of the water, it'll just leave and become oxygen gas. This is a big deal with the global warming phenomenon, or the ocean temperatures getting warmer. If they're getting warmer, they can't hold gases. If they can't hold gases, then fish can't breathe. Right here. Here's the science. Oxygen percent goes down as the water gets warmer. So if there's a point where there's not enough oxygen in the water for fish to breathe, the fish die, and that's bad. Here are solids, whereas you increase the temperature of the water, the ability for the water to pull them apart increases. All right. So basically, we're just going to need to be able to read one of these solubility curves. I will give you a temperature and ask you whether it's going to be saturated or unsaturated. And the key here is you just find the line. And if the solution's below the line, it would be unsaturated. And if the solution's above the line, it would be saturated. Let's try one here. So how many grams of potassium nitrate can you get at 45 degrees? So potassium nitrate, potassium is K. So potassium nitrate can either be this blue one, this green one, or this purple one. And of those three, even though you didn't learn these, you know nitrates have N's, so that's probably this one. So at 45 degrees, the maximum amount, 45 degrees down here. At 45 degrees, the maximum amount of potassium nitrate you can get in the water is ballpark 75 grams. So you're just going to use that to figure out how many grams you can get in that. So which of these is least affected by temperature? So of everything on this graph, you'll notice a lot of things keep going up or some things go down. Ammonia is a gas, so it's going down. SO2 is a gas, so it's going down. But the thing least affected by temperature seems to be salt, NaCl, the actual table salt. No matter what the temperature, it's pretty much a little bit below 40 grams per 100 grams of water. And, okay, so what kind of solution would you have if I said you had 60 grams of NH4Cl at 50 degrees temperature? So at 50 degrees temperature, you had, I forget what I said, 60 grams maybe? I thought I was trying to go above. So if you tried to get 60 grams of NH4Cl at 50 degrees Celsius, it would be, it's beyond saturated, right? 10 grams of it won't even get in there, if that makes sense. And then if you had like 20 grams of KCl at 70 degrees, so 20 grams of KCl at 70 degrees, that is below the line, so that would still be an unsaturated solution. All right, so you'll have some chance to do that. Just like with doing reactions, the way to increase solubility, you agitate it, right? If you stir things, they tend to dissolve better. If you crush them up into smaller pieces, they tend to do better. And if you increase the temperature, solids will tend to go in there better. All right, so the other thing you need to know is what we were doing last week, that molarity is moles over liters. So there's two ways to deal with this. You can either be given a solid, right, like we did with hot chocolate or drink mix, and there's a certain amount of solids, a certain amount of grams, and you're going to dissolve that in a certain amount of water. So you need to turn your grams into moles, and we do that on the periodic table. So sodium on the periodic table is 23, and chlorine is 35.5. So you add those up, and you just do that. 5, 8, and that's 58.5. So the units of things from the periodic table are grams, so 58.5 grams in 1 mole. And so you're just going to divide 25 by 58.5, and that'll give you the moles of salt, which is 0.427. So that's moles, and then we want to divide it by liters. And right here it was given to you in liters, so you're going to divide by 2.50. Oops. 2.50 liters. So moles over liters. If this was given to you in milliliters, you would have to do the 3 move. But since that was liters, we didn't have to do that. So we just divide 0.427 by 2.5. This is a 0.17 molar solution. All right. So a 0.17 molar solution of NaCl, if we go back to this, is going to look like 0.17 molar solution of NaCl would look like, oops, a little too much. All right, so it's going to look like basically that. All right, so that's 0.1. So it's still capable of taking more salt at that point, right? It's nowhere near the saturated point. It's perfectly fine to do that. So you take the grams, you just put them in the moles, and then you divide by the liters. That's if you have a solid. Sometimes you need to do it backwards. If you need a certain amount of solution that is 1.25 molar, so let's say you need 3 moles of KNO3, 3 liters of KNO3 solution, that's 1.25 molar. So 1.25 moles per liter, right? That's moles per liter. If we multiply that by 3 liters, liters will cancel and that'll give us the moles. So 3 times 1.25 is 3.75, and that's how many moles you need. 3.75 moles. And then we would need what KNO3 weighs, which is a potassium, right? A potassium, a nitrogen, and 3 oxygens. So 16 times 3 is 48, and there's 1 nitrogen is 14, and 1 potassium, which I think is 40. I'll look that up real quick. Potassium mass is 39, yeah, so 39. So then you add all that up, and 39 plus 14 plus 48 is 101. So it's 101. So if you need 3.75 moles and each mole weighs 101, you would have 378 grams is what you would need, because that is 3.75 moles and it's 101 grams in 1 mole. And that gives you 378 grams in 1.25 molar. All right. The other thing we did is if you have a pre-concentrated solution, like a flavor enhancer, then you use this equation, M1V1 equals M2V2. In this case, you need to just have some amount of some concentration, and you're trying to get another amount of a different concentration. So how many liters, there's your X, of means times, right, times 12.0 molar. So 12.0 times X equals 1.25 of means times. So you're going to have X times 12.0 equals 1.25 times 3.25. So that's how you do these types of problems, okay? You just basically, and what they're referring to is this pre-concentrated solution, just like when you did this. Actually, just like when we were doing this, that would be the equivalent of using this dropper, okay? And the dropper has concentrated solution in it, and as you add it, the concentration is going up because this is pretty concentrated. All right, so that's all we're doing this week. Answer some questions on a Google form, and that should help you. Let's just finish this real quick. So what we said is it's 12.0x equals 1.25 times 3.25. So 1.25 times 3.25 is 4.06 equals 12x. So x is going to equal 1/3 basically, or 0.338. So it takes 0.338 liters of 12 molar HCl in a 125 liter container to make a 3.25 molar solution. All right, that's all I got for you today. Do the Google form as often as you need, and enjoy spring break.